Welcome to this talk of Contactless Vital Signs Monitoring by mmWave Efficient Modulatorless Tracking Radar. I am Wael Abdullah Ahmed. I have participated in this work while I was with IHP, also Jinghaolu, and Batu Hansutbas, now with IHP, under supervision of Professor Hermann Jali Ang from Karlsruhe University of Applied Sciences and Professor Dietmar Singer from Ulm University, both from Germany. After a brief introduction and showing the motivation behind this work, I will show the concept we are trying to build, and then I will discuss the architecture of the radar, and I will discuss the proposed antennas to build this architecture, and I will show the prototypes we have built and the measurements we have done before I conclude my talk. Let's get started. So, millimeter wave radars now are emerging our lives in multiple domains in many applications. For example, measuring the microdoppler vibrations or measuring the range with very high accuracy. Here, for example, at 2 meters, we can measure this range accurately with an accuracy of less than or better than 10 microns. This might be very useful in metal machining, where the cutting depth can be measured remotely by the radar. Another important application is measuring the liquid levels inside cement factories, for example, where the temperature is very high and the environment is not suitable for other sensing technologies. Not to mention the medical and automotive applications. Here we are targeting medical applications. We would like to measure the vital signs of multiple patients using low power efficient compact radar, as I will show. In general, we are building multi-mode scalable radar sensors based on this multi-mode architecture, which is based on a single LO whose frequency is relaxed by a frequency multiplier. Then it's split between TX path and RX path, both with modulators. These modulators define the required radar technique, CW or FMCW or PMCW or even MIMO, with different schemes, time division multiplexing or frequency division multiplexing or even code division multiplexing. And according to the radar technique, the radar can sense the presence of an object, its range, its angle, so one-dimensional position or two-dimensional position, and its velocity if it's a moving target, or its vibration rate if it's a vibrating target. And the scalability in the system is built based on a single transceiver that routes the LO input frequency to the output so that it can feed another channel, building a daisy chain, so we can build multi-channel radars or large MIMO radars to measure two-dimensional position with high angular resolution. Synchronization between LO inputs at different channels can be done in the digital domain using the single LO architecture. Here we are proposing a concept that uses the bandwidth, the available bandwidth, to measure the angle with high angular resolution rather than using the bandwidth for range resolution. This can be done by employing a leaky wave antenna whose beam is scanned without modulators in the TX path, and it allows the radar to estimate the direction of arrival without multiple receivers, only with single receiver. I will talk more about the architecture in this section. So the concept is to utilize the available bandwidth of the circuits or the regulated bandwidths in the frequency range to scan the beam, the TX beam, and measure the angle from the reflection from the target, so the direction of arrival, using only single receiver. And this can be used only in Doppler radars. So to measure vital signs, for example, only CW signal is required. The range is not required in such an environment. Suppose a multi-patient hospital room with multiple beds. So the room height is fixed and beds heights are also fixed. So the range information is not important, but the most important is measuring the vibrations or the vital signs from these patients. So instead of using the bandwidth for range resolution, we would like to use the bandwidth for angle estimation so we can sense multiple patients using the single radar. According to the antenna characteristics, we can cover a certain space, certain angular range, which is defined by the room size. For a single patient, we need a very narrow beam so that it does not couple to the other patients, adjacent patients, and also the antenna should be with a single beam, should be a single beam antenna without other lobes or side lobes, not to interfere with other adjacent patients. The transceiver we are using to implement this concept is based on a single LO, which is also relaxed by a frequency multiplier, and it's split between TX and RX. The TX is as simple as an amplifier, and the RX is as simple as a mixer. Here it's IQ mixer. And two antennas building bistatic radar at TX and RX can synthesize the complete radar. Since the number of components is low, we can integrate the frequency synthesizer in the chip. So this very low number of components can save a lot of chip area, silicon area, and also a lot of power consumption. There is no modulator in the TX or RX. For the antenna, as I mentioned, single beam antenna should be used, and the beam should be narrow in the azimuth so that it covers only the space from a single patient. Let's imagine the environment of a multi-patient room, and the sensor is put in the ceiling, and now the radar is configured at this frequency or at this angle. Another angle, or if we just scan the frequency, the LO frequency of the radar can focus on another patient, another space, and also another one. So according to the input frequency, the beam is scanned toward a certain direction, and the receiver is sensing from a certain location. According to the available bandwidth, we can define the angular range, and the beam width should be as narrow as possible, not to interfere with adjacent targets. The ISM band at 60 GHz is from 57 GHz up to 66 GHz. So with such antenna, we can cover only 31 degrees based on the available regulated frequencies. Here I am comparing two transceivers. The normal transceiver we are using for the multi-mode architecture and the proposed one. We can see we saved all the modulators in the TX and RX. Here we were using two BBSK modulators. Also, we saved the LO routing path, the LO redistribution network here. A lot of components were saved and a lot of input ports also. So we are saving a lot of chip, silicon area, and power consumption. 64% less power consumption can be achieved even after integrating the frequency synthesizers. We are putting LNA here instead of PA because the regulated power is only 10 dBm effective isotropic radiation. We propose to use leaky wave antennas to build this concept. We are proposing two leaky wave antennas. The first one is based on 15 series fit patches, as shown here. The patches are designed at 61 GHz. This is the radiation pattern, simulated 3D radiation pattern at 61 GHz. The 2D radiation pattern cuts can be seen here with a half power beam width of 10 degrees and 158 degrees. And the scanning range in the ISM band can be from minus 40 degree to 70 degree, from 57 GHz up to 66 GHz, with a scanning resolution of 3 degrees per 1 GHz. The antenna bandwidth is much wider than the available ISM bandwidth. It covers from 50 to 70 GHz with a peak gain as high as 14 dBi and a radiation efficiency as good as 70%. So the antenna bandwidth alone can cover 60 degrees scanning range, but the ISM band only 31 degrees. And to increase the scanning range within the available bandwidth, we can increase the number of elements, or we can redesign it. And this is what we are proposing next. We have 40-cell Franklin leaky wave antenna. Xinghao Lu designed this antenna, and more analysis can be found in his journal article here. So the beam width is as narrow as 6 degrees, because we have 40 cells, and we can cover in the ISM band 61 degrees scanning range from minus 20 degree to 41 degree with a scanning resolution of 7 degrees per 1 gigahertz. Also, the impedance bandwidth is much wider than the available ISM band frequencies. We can simulate the multi-patient room again with this antenna. So we would cover an angular range from minus 20 degrees at 57 gigahertz up to 41 degrees at 66 gigahertz with a beam as narrow as 6 degrees. So we are guaranteeing that no interference would occur between the adjacent patients. And we are covering 61 degrees scanning range from the ISM band. Here is a comparison between the two antennas. Of course, the 40-cell one is much area consuming, but it covers wider angular range. We prototyped the patches one. Here is the prototype with a waveguide transition at 60 GHz for measurements. Here we are comparing simulated and measured S11. Both agree very well, and the radiation pattern here is measured across frequencies. We can see the scanning profile. The gain is as high as 15 dBi, and also we are comparing here the peak gain over frequency simulation and measurements with a good agreement. We use this antenna to build this radar sensor. Two antennas, TX and RX, built a bistatic radar with a 60 GHz chip, and then we are building this experiment where the radar is facing a vibrator, which is a loudspeaker here. We can load a 100 Hz tone for the speaker, and then we can detect the vibration due to this tone by the Doppler radar. Here we detected the 100 Hz loaded tone and its harmonics. Now if we scan the frequency of the radar, then the radar would scan the area, and only the peak would be detected at a certain frequency, which corresponds to a certain angle of the target. And then if we have multiple targets, we can scan the frequency and get the peaks at these frequencies, which correspond to the locations of these targets. And this is the scanning profile we built. Scan the frequency from 50 to 70, and we can get the peaks only at certain angles where the vibrators are. To conclude, we propose to use a leaky wave antenna to scan the beam to detect multiple targets using single channel, and this single channel would save a lot of area and power consumption. We prototyped one leaky wave antenna, and we built this radar experiment. Thank you.